The Human Experiment by Dr. David Carmichael, Chapter 7, The Material Record. In previous chapters, we have focused on the philosophical arguments and genetic evidence for human evolution. However, much of the evidence for human evolution comes in the form of material remains. These include the preserved remains or fossils of organisms and the material byproducts of human behavior in the form of artifacts. The human species is a product of both biological and cultural evolution, but biological changes played a more prominent role in the early evolution of humans, while cultural changes have dominated the more recent developments that characterize our species. Both biological and cultural changes are documented most entirely by the physical byproducts of humans and their behavior that compromise the paleoanthropological and archaeological records. This chapter will provide an introduction to the basic steps involved in fossilization, an overview of how paleontological and archaeological sites are discovered, and a summary of the types of dating methods that researchers use to determine the age of fossils and sites. Question answer. How do we know that there were ancient human ancestors? Answer. Fossils provide the evidence for long-term evolutionary change, and scientists use a variety of dating techniques to determine when those ancestors existed. The fossilization process. The process of fossilization is complicated and perhaps fairly improbable, making the formation of and discovery of fossils, especially those of terrestrial vertebrate animals, are relatively rare event. There are three different sorts of fossils that are commonly used to study human evolution: true form fossils, trace fossils, and casts. True form or replacement fossils are those formed when minerals seep into the remains of a plant or animal and replace the organic remains. This process is sometimes called petrification, and petrified wood is a well-known result of such fossilization. The most common fossils, bones, and teeth, are also formed by this replacement fossil. Figure 7.1. Trace fossils are impressions left in soft sediments by plants or animals are subsequently hardened through mineralization. Footprints are trace fossils that may provide important information about the soft tissues of the feet, as well as hints about the social behavior of some humans and human ancestors. Cast or mold fossils are those which result from a negative impression being filled by sediment that is later hardened, producing an imprint of the original surface. Casts of the brain, surface, morphology, and the interior of skulls are mold fossils, of particular interest in the study of human evolution. There are several steps that are necessary for a fossil to form and become part of the database of biological change. If any of the steps are interrupted or prevented, the remains of the organism will be unavailable to science. Figure 7.1. Go ahead and scooch on that. The first thing must happen is the preservation of the organisms. In most cases, this means the organism must be buried to protect it from the elements. In order to be most useful, burial would need to happen quickly, enough to protect the remains from excessive deterioration, but gently enough that the deposition of sediments doesn't cause too much damage. If a body is exposed on the ground surface for any length of time, it will likely be damaged and scattered by scavengers. If it is uncovered for a long period, it will become weathered, often cracking and breaking up into splinters. If it sits on the surface long enough, erosion might even scatter the pieces. Eventually, they will be completely decomposed as a result of weathering. Ideally, sedimentation would occur fairly quickly but gently. If the organism dies in a high energy environment, such as along a major river, the carcass or bones may be broken up and scattered by erosive force of a high energy flood. I think that says incorporating the fragments into the gravels of the stream bed, where they will be further damaged. Perhaps the best locations for fossils to form is in low energy depositional environments such as swamps, sloughs, lakes, and slowly moving streams, where fine-grained sediments, silt and clay, are deposited gently around the remains without disturbing them. Another sort of deposit conducive to fossilization might be volcanic ash, as long as the organism is near enough to the eruption to be gently buried in ash and far away enough that it is not destroyed by the pyroclastic debris flow. The next step is the actual fossilization, meaning the replacement of bone or other organic parts by minerals. This process usually involves the dissolving of minerals contained in the surrounding sediments. The minerals in solution then percolate through the sediments and replace the organic parts of the bone. Molecule by molecule, an alternative and potentially more rapid process may result in fossil casts or prints. When organisms are buried by sediments that solidify quickly, or when such sediments are imprinted, decompose, the latter situation is what preserved the Australopithecus footprints in volcanic ash at site of the Latoli, Tanzania, and the Homo sapiens prints in gypsum mud at White Sands National Park in New Mexico. See figure 7.2. Some kinds of rocks and sediments are more likely to contain fossils than others. Fossilization will be favored when environmental conditions are conducive to the formation of sedimentary rocks that are highly mineralized, containing materials that can be dissolved and redeposited in the fossils. Basalt and other igneous rocks that are deposited as flows are not likely to contain fossils because the organisms would have been melted or burned by the intense temperature of the molten rock. However, volcanic ash falling gently at some distance from the volcano could readily produce fossils. Sedimentary rocks such as limestone, shale, siltstone, and sandstone can all contain fossils, but the gentler depositional environments represented by the finer grained rocks may yield more intact specimens. After a fossil is formed, usually while deeply buried by the surrounding sediments, it must be uncovered or re-exposed. The process involved could include faulting, uplifting, and erosion by wind and water. They must be sufficiently strong to actually expose the fossil, but ideally not so strong that the fossil is crushed, scattered, or carried away from its depositional context. And finally, the fossil must be discovered by someone who recognizes it for what it is and enters it into the fossil database. This final step may seem easy, but it is really not so simple. Imagine looking for a piece of a fossilized bone the size of your little finger, distributed amongst thousands and thousands of other rocks. I'm sorry, I got lost. Thousands and thousands of other rocks and stones. So sorry about that, guys. Scattered across an area the size of several football fields in the middle of the wilderness in 120-degree heat and glaring sun. It would be easy to overlook small fragments, especially if they are still partially buried. What if the fossil were discovered by someone else with different interest? The discovery of Homo erectus fossils from Zogadoon cave in China occurred after scientists spotted hominin fossils in the window of a traditional Chinese apothecary shop. The fossils were being sold as dragon bones to be ground up and used as an ingredient for of aphrodisiac potions. Clearly, someone had been aware of the fossils and the site of their origin. For some time, they were not part of the fossil record of human evolution until researchers studied them. Given all the steps an organism must go through to become part of a fossil record, it's remarkable that we have as many hominid fossils as we do. You may recall from Chapter 2 that there are only about 36 known specimens of Tyrannosaurus rex or T. rex. Nevertheless, most of the public has no doubt that T. rex actually existed. There is much more fossil evidence for our hominin ancestors, as will be discussed in Chapter 8. There are more than 8,000 fossil specimens of hominins, many of which are transitional, exhibiting ape-like as well as human-like characteristics. How is material evidence discovered? In Chapter 3, paleoanthropological and archaeological fieldwork was likened to the forensic analysis of modern crime scenes. In many ways, this is a valid comparison, but prehistoric fossils, localities, and archaeological sites differ from modern crime scenes in several ways. The most important difference is that prehistoric sites have not been identified ahead of time for the investigators, and they may still be buried. That is, the paleontologist and archaeologist must locate the site before any material remains can be recovered and studied. Locating sites, especially in remote and undeveloped regions or in areas of extreme natural conditions, can be very challenging. The process of finding and identifying the places containing fossils or human artifacts, is usually called a site survey. Most archaeological or fossil sites are discovered during pedestrian survey. By simply walking across the land and carefully examining the ground for the material remains, one would also examine erosional cuts, rodents, burrows, and anthills, where evidence of buried materials might be exposed. If one is already familiar with some locational details the materials being sought, fossils from a certain time period, for example, that knowledge can be used to focus the search on the geological layers containing fossils of the appropriate age. If no one knows that early hunter-gatherer groups in the American Southwest tended to locate camps on the downwind side of former lake beds, that observation referred to as Southwest tended to locate camps referred to as site pattern recognition, may be used to identify places where one is likely to find additional examples of such sites. However, if one doesn't have that sort of prior knowledge, or if one is interested in learning about other kinds of sites that may occur in different settings, it will be necessary to search more of the landscape. The landscape is a big place, and as we will see in Chapter 12, prehistoric populations were highly mobile and used large portions of the landscape. Therefore, if one's goal is to understand people in particular time and place adapted to their environment, it might be necessary to search entire valleys or drainage basins for evidence of their activities. In these sorts of cases, it's necessary to look at only a portion of the landscape by conducting a sample survey. Samples can be selected in a variety of ways, but we are primarily interested in obtaining a sample that is representative of the areas or sites that are being investigated. To ensure that the samples are representative, it is often necessary to examine a stratified sample in which the land areas sampled are distributed among the different landform or terrain features that might contain sites. Some large survey areas may be examined in their entirety, but in most cases, only a small fraction of the area will be walked. The surveyed areas will usually be statistical samples contained on a grid, square, or linear transects. Kelly and Thomas, 2014, 41, Judge, 1981. It is increasingly becoming the case, at least in archaeology, that aerial surveys are being used to study large project areas. A variety of remote sensing technologies are being used to identify sites when survey areas are very large or very remote, or occur in areas of heavy ground cover. Figure 7.4. Low and high altitude photography can be effective with or without infrared recording. Radar techniques such as light detection and ranging, or known as LiDAR, can be used to enhance and map subtle ground features, or to record and record surfaces and sites. Oh my goodness gracious, I'm so sorry today, guys. Surfaces and sites that are obscured by vegetation. Other methods such as ground penetrating radar, GPR, and proton magnetometer survey can detect buried features that exhibit little or no surface manifestation. While remote sensing techniques can be very useful in locating sites, they do not replace the need to actually visit the sites on the ground to verify their contents after they are discovered. Here's a close-up. And then here is this picture. Although the features delineate in figure 7.5 were discovered by remote sensing, it was a test excavation that revealed the details necessary to identify them as house floors and a wall trench. Oh, here's a close-up of that. How old is it? One of the biggest misconception to the general public has about paleoanthropology and archaeology is the notion that we can't know the date or age of a fossil or prehistoric fact. Many people seem to think that scientists make hunches, guesses, or wild speculations about the age of prehistoric materials. Perhaps this misconception is a specific case of the general misunderstandings about the use of indirect evidence that we discussed in Chapter 3, or perhaps it relates to some people's belief that Earth is only a few thousand years old. For such believers, any scientific evidence for an older Earth must be dismissed out of hand, and that perspective has some currency in today's public policy discourse. I prefer to think that many people simply haven't been introduced to the science behind geological and archaeological dating, and I hope that when you hear about some of the details, you will be able to see how scientists are often able to reliably date prehistoric events and materials. The geological timescale is completely beyond the personal experiences most people have with the passage of time. So it is hard for most of us to think about ancient time periods. I'm sure most of you reading this book don't remember the Vietnam War. That reality always reminds me how old I'm getting, but it also illustrates that for most of you, the experiences of the 1970s are just things you hear about from when you're older relatives or read about it in history books. For most of us, something our grandparents tell us about their earlier years is what we might consider old. And if something is so old that your grandparents didn't experience, then it is really old. But of course, the past 100 years is merely the blink of an eye in geological and archaeological terms. To help people visualize the age of the Earth in understandable terms, Carl Sagan, 1977, developed the idea of the cosmic year, which reduces the entire age of the universe down to a single year. Figure 7.6, the cosmic year begins January 1st with the Big Bang and ends with the present on December 31st. Each day represents 42 million years. On one hand, we can see that most of what has occurred on Earth happened long before humans or our hominin ancestors even existed, the last 200,000 years, during which time modern humans evolved, represents only the last 2 minutes of the cosmic year. Nevertheless, 200,000 years or even 20,000 years is far older than most people can imagine or comprehend. How can we know about these ages? Here's the cosmic cavern. There are two different kinds of broad categories of prehistoric techniques: relative dating and chronometric dating. Relative dating techniques do not provide a definite age in years, but they order events, fossils, and artifacts in a sequence of relative age. In other words, it is possible to know that something is older or younger than something else without knowing by how much. In contrast, chronometric dating methods provide an estimate of the age of a fossil or artifact in years, often with an error factor that indicates the degree of confidence one has in the estimate. A variety of dating techniques are listed in Table 7.1. Each of these techniques has specific applications, strengths, and weaknesses. However, by using multiple techniques, when possible, and cross-checking them for consistency, geologists, geophysicists, geochemists, biologists, and anthropologists have built up a global chronological framework about which there is a high degree of agreement and confidence. Most relative dating techniques are related in one way or another to stratigraphy. So it is useful to briefly mention how that works. Stratigraphy is based on the law of superposition, which states that Earth's layers, rocks, and soils are deposited with the oldest layers on the bottom and successively young layers on the top of one another. Barring any major disturbances, we can confidently tell which sediments were deposited and what order. By extension, the relative ages of fossils and artifacts contained within the different stratigraphic units can also be inferred. However, even though we know the relative ages of the sediments and their contents, we don't know how old they are in years or precisely how much time has elapsed between the deposition of different layers. As an example, consider the stratigraphy shown in Figure 7.7. These sediments are exposed by erosion throughout the Palo Duro Canyon State Park in Texas. The layers labeled A and B are the oldest, and they are part of the Quartermaster Formation, which dates to the Upper Permian period, circa 299 to 251 million years ago. The overlaying layers are a part of the Upper Triassic Dockham group from about 237 to 201 million years ago. They are labeled in ascending order from bottom to top to reflect the order in which they were deposited. Initially, the units were defined on the basis of their contents, such as fossils, mineral composition, etc. Only later were the estimated ages in years determined by the use of the chronomenic dating technique called potassium argon, K and AR, Dating International Commission of Stratigraphy 2020. Geological strata and early fossils are generally dated with the KR technique, which is well suited to dating volcanic materials like other radiometric dating techniques. It is based on the rate of radioactive decay of one element into another. Different elements have different half-lives and are therefore appropriate for use on sediments from different time periods. Radiocarbon or carbon 14, which is C14, dating is the preferred method of dating organic materials in archaeological sites dating to past 75,000 years. It is also the technique about which members of the public are most likely to have heard. Although C14 dating is rather precise and its validity is widely accepted among researchers, it is often misunderstood or misrepresented by the general public. So let's go through a brief introduction about how it works. Radiocarbon dating is commonly misrepresented in at least two different ways. Some researchers refer to C14 and similar dating techniques as absolute dating, and people often conclude the dates derived from these techniques must be exact. This is not true. Most chemometric dating techniques, my preferred terminology, yield estimates of dates, albeit precise estimates. The other more common way in which radiocarbon is misrepresented is in the claim that C14 dating simply cannot be correct. This claim is most often associated with young Earth creationist beliefs about the age of the Earth being no more than 6,000 years to 10,000 years old. Believers in a young Earth have made many statements about how and why C14 dating must be wrong, and how scientists are fooling themselves about the age of the Earth and thus the validity of evolution. The failure of such arguments becomes obvious when one knows something about the history of the development of radiocarbon dating and other radiometric dating techniques as well. Here is the table. Here's another on the chart. Radiometric dating techniques are based on the concept of radioactive decay, a natural process that can be used as a sort of atomic clock. The time range of applicability is determined the date of the rate of radioactive decay, the half-life of the element in question, 5,730 years. In the case of radiocarbon, Willard Libby was the scientist who initially worked out the rate of radioactive decay for C14. It is significant that Libby's method grew directly out of the work he and other chemists did on the development of the atomic bomb during World War II. Larson, 2017, 254 to 255, That is, radiocarbon dating is a direct peacetime application of knowledge gained about subatomic particle physics during the development of atomic bomb. For Chapter 3, you know about the principle of uniformitism or actualism. You will recall that uniformitism is the idea that the process at work in nature today are the same as the ones that operated in the past. Another expression of this principle is that natural processes that work in physics and in chemistry are also at work in biology and anthropology, or any other scientific discipline. So if one denies the radiocarbon dating is valid, one can also denying the existence of the atomic bomb. The two applications are based on the same principles of subatomic particle physics. One cannot have it both ways. One cannot logically argue that the atomic bomb is real, but an ancient Earth is not. The physical principles of radioactive decay are either real or they're not. One doesn't get to choose when they work and when they don't want them to work, simply because we may be uncomfortable with the implications, such as an ancient Earth. It is even more ironic to use the medium of television or the internet to broadcast such a message. Because television and monitor technology is based on subatomic physics too, television screens and computer monitors, or at least using pre-liquid crystals display, the LCD technology, contained a cathode ray tube that used an electronic gun to spray electrons into a photosensitive screen to produce the image. The technology is another of the peacetime applications of the knowledge gained about subatomic particles during the development of the atomic bomb. So if the physical principles were not real and understood, the technology wouldn't exist. We humans don't really have that choice in a logical word, but the process of nature work, or they don't. We don't get to decide when we might like to suspend the laws of nature. So accepting that archaeologists really can date prehistoric materials using radiocarbon, just what do the dates mean? Simply put, a properly reported radiocarbon date gives an estimate of the date with an error factor, which specifies the degree of confidence in the estimate. We can think of it as something like a voter poll taken during political campaign. Is there a way we can know for certain who wins for election? Yes, we can wait until the election actually happens, do an accurate count of the votes, and announce the winner. Then why conduct surveys and polls before the election? Because someone such as candidates and their campaign staffers want to know ahead of time if there are any trends that might need to address before the election, but pollsters can't actually contact all the voters and record their choice. That would be called an election. Instead, they contact a sample of likely voters and make a reasoned estimate of the distribution of votes, accompanied by an error factor. Because if the pollsters are unwilling to wait for the election, their projections are necessary based on a sample of the voters, and therefore there are sources of error associated with the estimate. Similarly, in the case of radiocarbon, the only way to know for certain how much C14 is still contained in a piece of old charcoal would be to wait for all of the C14 to decay, counting each release of a radioactive particle as it occurs. But in order to count each one, we would have to be counting for thousands of years. Instead, we count a sample over a period of several days and make an estimate based on that sample. That interpretation or meaning of that estimate can be understood by reference to the normal distribution in figure 7.8. Let's use simple data as an example. 1,000 plus divided by negative 50 years before the present. What this really means is that the estimate of 1,000 years corresponds to the mean of mu, of the normal distribution. The error factor of 50 years corresponds to the standard deviation around the mean of -1 0 and +1 0 error. The range of values within one standard deviation of the mean corresponds to 68% of the area around the curve. Therefore, the reported radiocarbon date really says here is a 68% chance of the actual age of the dated sample is between 950 and 1,050 years ago. Now, in statistics, as in weather forecasting, most of us would like to be more than 68% confident about our results. So the 95% confidence interval is used by expanding the confidence interval to 2 standard deviations, -2 and 2 + 2. We can include 95% of the area around the curve. Thus, what this date estimate really tells us is that there is a 95% chance that the true age of the sample is between 900 and 1,100 years old. There are other issues involved in the use of radiocarbon that bear on the interpretation and reporting of dates. For example, radiocarbon dating can only be used on samples containing organic material. If someone tells you that stones were dated directly using C14, they are misinformed. Radiocarbon can be used only in samples of organic materials such as charcoal, wood, paint, plant fibers, shell, soil, carbonates, etc. Things like stone artifacts can only be dated indirectly by C14. When they are in close association with organic materials, it is also important to remember that radiocarbon dates the death of an organism, not the time when it was actually used by humans. For example, if a timber was cut for prehistoric construction and it is eventually dated by archaeologists, we will get a date on when the tree was killed, not when the timber might have been recycled and reused during later periods of construction. As noted in this is a really important graph. This is called a bell graph. I remember this from statistics. As noted in Table 7.1, there are also time limits to the usefulness of radiocarbon. This is because after 50,000 to 75,000 years, the amount of C14 remaining in a sample is so small that it can't be accurately measured. So if someone alleges that bones have been dated to 500,000 years ago using C14 technique, they are mistaken. Potassium argon dating could be used on fossils and sediments of that age. However, we also know there have been fluctuations over time in the concentration of radioactive carbon in the atmosphere, and therefore in the organisms living at those times. By extensive radiocarbon dating of wood samples of known age, cross-checked with the dendrochronology, figure 7.9, we now know that prior to 1500 BC, radiocarbon dates are about 150 years to young. By 4000 BC, they are about 700 years too young. Correction factors have been derived from the dendrochronology dates as far back as about 11,300 years ago. Ashmer and Sharer, 2164. While each of these challenges or limitations might seem to make radiocarbon dating less reliable, the opposition is actually the case as we develop ever more detailed understanding of the advantages and disadvantages of this or any technique, the result that derive from their more informed use or more reliable. Here's figure 7.19. That's at Yosemite National Park. So I hope you can see that. This is the end of chapter 7.